Alright, y'all, so here it is. My ultra fabulous space mission to the big bad Ganymede. So, why do we care about Ganymede? And what is Ganymede? Well, Ganymede is the largest moon of Jupiter. In fact, it's the largest moon in our solar system. At 5,268.2 kilometers in diameter, it's actually larger than the planet Mercury. However, it's only about half as massive, with a mass of approximately 148.2 sextillion kilograms. Which, yes, seems like a lot, but comparatively, it's not that massive. Ganymede also has its own magnetic field, which is likely due to it having a liquid metallic iron core. It consists of three main layers, the metallic core being the first, and then a shell of mostly rock that surrounds the core, called the mantle, and an additional shell of mostly ice surrounding all of it. This outer shell is estimated to be about 800 kilometers thick. After that, there's evidence of a massive ocean in between the layer of thick ice above the mantle and another layer of ice which constitutes the moon's surface. It's kind of like the planet Camino from Star Wars, but, without the life-sustaining atmosphere and the endless storms and the unfrozen oceans. Okay, so it's not like Camino at all, but it's still pretty cool. Anyway, this ocean, which is more or less confirmed, would easily have much greater volume than all of the water on Earth. This ocean is mostly confirmed due to the auroras that exist above the surface of the planet's icy crust. These auroras are similar to the ones that we have on Earth, like the Northern Lights. Which brings me to my next point of why do we care? Well, all this information leads to a possibility of Ganymede being inhabitable, which is big news. Of course, for life to exist or even begin here, there would need to be millions and likely billions of years of changes to the planet's surface, atmosphere, and its temperatures. Already there's theories of a thin layer of oxygen in the otherwise absent atmosphere, but nowhere near enough to harbor life. So, how do we get there? And more importantly, what do we accomplish by getting there? Well, if a craft is going to be funded and built, which can cost billions of dollars, then it should likely be capable of multiple tasks. For instance, more in-depth topographical analysis would result in greater depictions and understanding of the moon's surface. Taking samples from the surface and analyzing the composition of the material, analyzing the atmosphere to determine what it's composed of, if anything, since there's only evidence of a layer of oxygen, and maybe truly identifying if the ocean beneath the crust exists. Yes, it was essentially confirmed, but nothing quite says "I told you so," like obtaining hard data. Discovering actual ranges of temperature throughout Ganymede's orbit around Jupiter would likely be a relatively easy data point to obtain as well. Essentially just like what we did on Mars with the rover and all that. And of course, by achieving this feat, we would effectively set up the basis for future missions to Ganymede, if of course it proves to be worth our while. So, how do we get there? Well, with engines. The payload will be aboard the rocket Titan 401B Centaur, which is a three-stage rocket that was used with the Cassini-Huygens, sorry, don't know how to pronounce that, which was a spacecraft satellite that orbited Saturn and its moons. The first, or 0th stage of the rocket is the primary thrusters, which gets it off the landing pad. These two strap-on SRMUs provide 7.56 meganewtons of thrust. The actual first stage will be two standard LR-87 liquid propellant rockets that provide a combined 3,800 kilonewtons. Stage 2 will be two standard LR-91 liquid propellants that provide 467 kilonewtons. And finally, the third stage is the Centaur T component with two RL-10s that provide 110.1 kilonewtons. And this will be used as a final push out of Earth's orbit and into the far reaches of space, with trajectory towards Ganymede. We'll also need power. Since there won't be much sunlight, we'll need radioactive batteries, such as the multi-100-watt radioisotope thermoelectric generator, or MHWRTG for short, because nobody wants to say that whole thing. These bad boys were used in threes on the Voyager 1 and 2 satellites. They provided about 158 electric watts per generator, and they individually weigh approximately 37.7 kilograms. The radioactive isotope used has a half-life of about 87.7 years, so obviously pretty long-lasting. But we may need more than 3 since this will ultimately be a rover and not a satellite. For shielding, I'm wanting to use the same aeroshell shielding that was used for the Mars Spirit and Opportunity rovers on its path to Mars, or rather on their path to Mars. This consisted of a heat shield and a back shell, where the heat shield was used for the heat of entry and aerodynamic braking, and then the back shell carried the parachute and other components used for entry such as descent and landing by using rockets to stabilize the landing process and place the rover on the surface. So now, how do we achieve our goals? Well, for those of you who don't know what this image is from, or for those of you who know what this image is from, let's assume we can do a lot better. For those of you who don't know, don't worry about it. You're probably better off. So first, we'll need telecommunications to stay in contact and in control of the lander and rover. The telecommunications system will be taken from the Galileo spacecraft, which consisted of a radio frequency subsystem, an SX band 10 antenna subsystem, and an X to S band down converter. You can see on the figure that this is on the spun section. As a reminder, this will be used for the payload to land and for the rover to receive commands. It's not for a probe or satellite, as the image may depict. So how do we land this thing? With these big balloons, these airbags, specifically like the ones used yet again for the Spirit and Opportunity rovers. These reduce how careful and precise the tech has to be in order to achieve a non-catastrophic landing. And as we've seen previously, they're pretty effective. Also, it's just a wicked cool concept that we literally flung this thing into the surface and let it bounce around for a bit. Anyway, we'll certainly need analysis instruments in order to conduct our experiments. So we'll go ahead and use the Opportunity rover again, since that's the latest rover to have been used on another celestial body. The instruments will include a panoramic camera, or PanCam for short. These are 2 cameras to take detailed 3D panoramic pictures surrounding the rover. We'll use a microscopic imager, which is a high-resolution camera for magnified views for rocks and soils. We'll use a miniature thermal emission spectrometer, which measures spectrums of infrared light emitted from minerals in rocks and soils. We'll use a Moss-Bauer spectrometer, which determines composition of iron-bearing minerals in geological samples. We'll use an alpha particle X-ray spectrometer, which examines the elemental chemistry by measuring different materials and their response to radiation, like the X-ray and alpha particles. We'll use a rock abrasion tool, which breaks rocks to get fresh mineral surfaces. A magneray, which collects dust while the rover is moving, which will be used for compositional analysis. And then calibration targets, which are varying instruments that determine colors, brightness, and other information from these other analysis tools. So we'll also need a way to modify and transmit the data collected in a way that is readable for us back on Earth. We'll use the telemetry modulation unit that was used on the Voyager spacecraft. The telemetry modulation unit and the modulation demodulation system collects engineering and science data measurements that are taken from other components like cameras, sensors, and onboard diagnostic systems, and formats them for transmission. This handles data at 10, 40, or 1200 bits per second, depending on how quickly the data is coming in. So now that we've established all of these possibilities, it's important to take time to consider some differences in getting a rover on Mars and on this particular stellar expedition. First and foremost, as it's quite obvious, Mars is much closer, so getting a rover on Ganymede would likely be immensely more challenging and require much greater diligence and precision to achieve something so miraculous. Ganymede and Mars likely do not have the same terrain, so we'd have to consider our options of rover translation. Seeing as it's likely an icy shell, perhaps studded tires would be more suitable, or even something like tank treads. We're also dealing with a moon versus a planet, which will obviously have different atmospheric conditions as well as different gravitational potential. So for example, the gravitational acceleration on Ganymede is only 1.43 meters per second squared, whereas Mars is 3.71 meters per second squared. As was previously mentioned, there wouldn't be any availability for solar charging, since Jupiter is so far away from the sun. Attempting to use solar panels would be essentially futile, unless we somehow design ultra-sensitive panels that could absorb UV rays from like 475 miles or million miles away. Not likely. We'd also probably need to have additional propulsion devices on the payload in order to ensure that we actually land on Ganymede, in which case using them at the exact right time would be an extra challenge that would certainly take a lot of time and consideration to achieve. So anyway, there you have it. That's my mission. I hope you guys enjoyed.